Where are you? Okay, so let's see here. Hard jump game part 5. I think the last one was a few days ago or sometime this week. And it was actually pretty straightforward. So let's see how this one is. Given an array, integers array, and an integer d. In one step, you can jump from index I to index I plus x, where I plus x is within the array, and 0 is less than x is less than equal to d. So I guess d is the kind of how far distance-wise it can move to the right, as long as it doesn't move out of bounds. And similarly, it can go leftwards as long as it doesn't go out of bounds. In addition, you can only jump from index I to index j if array I is greater than array j. So the value that you're jumping to is going down, strictly downwards, or strictly less. And array I is greater than array k for all indices. Oh boy. You can only jump from index I to index j if array I is greater than array j, and array I is greater than k for all indices k between I and j. Okay, I see. So you can only jump if you're jumping downwards and nothing in between them is bigger than the original spot. Yeah, okay. More formally, minimum of ij, min of ij is less than k is less than max of ij. Min of ij. Min of ij is less than k is less than max of ij. The smaller of the two indices is k. K is what? What is k? For all indices, k. Okay, is just the value between those indices. Okay, yeah. I don't know. I'm not sure why they need to include that. You can choose any indices of the array and start jumping between. Return. You can choose any index of the array and start jumping. Return the maximum number of indices you can visit. So if you start, what is going on here? So this is basically the heights of the values. You can jump at most 2 spots away. 1, 2, 3. So you visited 4 things there. Here, technically, you could, if this was 3 away, then this could have been 1, 2, 3, 4 or something like that. Or if it was 3 away, then it would be 1, 2, 3, 4, 5. I think 1, 2, 3, 4, 5. Yeah, if it's 3 away. So you can choose where you start, and you're trying to find the longest distance. Okay. So here the distance is at most 3, but you can only do, you can't really even jump because you can't jump downwards at all. And here you can visit everything, jumping downwards. Okay, so how to build this seems straightforward enough in terms of understanding it. So from 1, so I almost want to, I wonder if it's any different if I think about it from building bottoms up. So for any particular, from any particular spot, you can try to find the longest thing. So if you have yeah, my sense is working backwards, working from the end has a lower branch factor than working from the start. Because from the start, 14, there's a number of places that you can jump to. But if you start from the low spot, like the lowest value in the array, if you start from there, you know that the total length would be 1 because you can't go from anywhere else. And then maybe if you go from there and then you work backwards, so you know that this one has to be 2 because it can only go, it only reaches there. But then there might be gaps, maybe. There might be gaps. I wonder. Alright, let's consider the constraints here. There's only 1,000 places and values for 10 to the 5th. 1,000 places kind of indicates that this might be n squared. It's very small. So if I did something that was doable in n squared, could it be that I actually create a, for every index, the locations of all the spots that would jump down to it, like a list of all locations that jump down to it. That might work. That might work. So 4, I would add, ooh, that's kind of rough actually, right? I mean, I'd have to be pretty precise about how I construct the list. I mean, if I can do n squared, 1,000 times 1,000 is a million, right? It wouldn't be that bad. So for every index, construct the indices of neighbors that can jump down to it, and then work backwards. What happens if I have something like 1 1 30 30 5 4 3 and the distance is 1? Like I would have 1 and 1. They're the lowest values. They can't really jump into anything. At that point, I would have to do 3. Some other thing. Maybe I can still do that. 3, 4, 5. So it'd be 3, 4, 5, 30. Okay, let's just go ahead and just start by trying. for each index, find all neighboring index, or create list of neighbor indices that can jump to it. So it's basically the destination, or it's the source of the jump, source location, where the index is the end location. Okay, so that'll be a default dictionary. So jump from, maybe. And this is going to be a default dictionary list. And I guess I'll take n as the length of the array. And I guess this would be how do I want to structure this? So like if the index is index 3, height 6, it would need to include this. Maybe maybe I do 2 passes using some sort of monotonic stack. So 6, 8, 10, or 6, 8, 13. 6, 8, 13. I have to do a monotonic stack each way. Yeah. How bothersome. Okay. So for, let's say, for every index k in range n, so let's say the value, the current, I'm going to call this height, or maybe I'll call it current height, is going to be the array at this index. And then I'm just going to do the left side values. So this is going to be, or I'll start with the right side because that's easier for me to think about visually for every right index. So I feel like I'm probably going to do something inefficient here. So for every delta in range D, I think maybe it should be delta starts at 0, but it should be 1. Maybe I'll need to do delta plus 1. If must be increasing, huh? If array at delta at this index k plus 1 plus delta is greater than current value for the height, then jump from from k appends k plus 1 plus delta. I want to also make sure that it doesn't go out of bounds. So d can be up to the array length. I think what I'm going to do here is I'm going to do a small hack. So I'll do array dot extend by 0 times n. So that's going to basically have a bunch of 0 height positions at the end of the array. And that'll make those positions impossible to be jumped from, but also be within indexable without me having to double check the out of bounds. Having checked whether or not the k plus 1 plus delta is out of bounds of the original n. Okay, so I think that's fine, and then I can say current is now equal to this new height. Because that's the new height that needs to clear to jump from later on if I keep on going further to the right. So this is the delta for the indices to the right. This position has to clear this height. Then if it does, then I add to the list of things I can jump from that index. And then I add, and then I increase the height that needs to clear. And I think that's it. I think I need to add the left neighbors now. So similarly, I think it's going to be for delta in range D if array at k minus 1 minus delta is also greater than current. I need to reset current. And jump from this new index k plus k minus 1 minus delta. Current is equal to array at k minus 1 minus delta. I feel like this is really redundant because there's a lot of recomputation of things, but it is what it is. And I'm just going to verify that this is working correctly. So I'll go ahead and do for every, I'll just do a small print. For every index k in range, actually maybe I can just do print here. I guess it doesn't need a default dictionary if I know the indexes is the key. So maybe it should just be a 2D array of arrays. So jump from should just be a list for every k in range n, where n is the length of the array. Yeah, okay. And then this is going to be for every k in range n. Actually, let's go and print verification within the loop here. Print, let's say k, and oh, does work k colon and then jump from a k. think that works. I'll just return 0. Alright, 0 can jump from 2. Excellent. 1 can jump from 2 or 0. Okay, I think maybe I should do this leftwards and rightwards. So index 0 can jump from index 2, index 1 can jump from index 0 and 2, 2 can't jump from anything, 3 can jump from 2, 4, and 5, 4 can jump from 2 and 5. Okay, this all seems... 5 can't jump from anything, 6 can jump from 5 and 8. Okay, this thing seems all fine. Alright, so I have the indices I can jump from. I think I need to have maybe a heap. I can use a heap, or I can use a... Is it a heap? Or I can use a sorted list, where I need to process it based on stuff that hasn't been processed and stuff that has the lowest height. So do I want to store the height in a list? Okay, I think I need process is false times n. Indices. I think either of them could work. Heap or sorted list, and then some sort of queue. Alright, I think I probably just want a queue, or maybe a stack. Because I'm just going to be popping it off the stack then. Huh. Popping off the stack. Could I have a process stack that just pops? Could I have a process stack that just pops? Or does my process needs to be a heap? Does my process need to be a heap? Oh gosh. Oh gosh. So this thing adds, if I was at the 7, let's say I'm at the 6, adds 10 and 12. Then I'm going to update this. Needs to update the 7, 9, and 10. 6, 6. Yeah, it has to be a heap because 6 would push 10 and 12 into the stack, but then 7 needs to be processed before it process at 10. Yeah, so it has to be a heap. So it has a heap. Six. When the 6 process it, it goes this thing 1, this thing 1, 6, 0, this thing 1, this thing 1, and then 7, this thing 1, this thing 1. Nine would make this thing 2. So, okay, I think I need some sort of sorting of values. Probably just create tuples. Value tuples is going to be value comma index for every element, for every pair in the array. So here I'll just go ahead and do value tuples appends array k and k. And then afterwards, kind of want to just do this in reverse order and just pop. So val tuples dot sort reverse equals true. I guess maybe I don't need processed, do I? I guess I'm just going to be processing based on reverse order. Man, this is actually kind of slow, huh? I wonder. Now that I think about it. So 1, 7, 9, 10. Is there ever a point like if there's a 7 and a 13 here, would the 13 ever skip down to the 9, skip the 9 down to the 7? Probably not, right? So would it make sense to track 7 jumping from 13, skipping the 9? Or can I just ignore the jump from 13? Like if 7 was within range of 12, could I just ignore it and say that 12 would eventually just jump to 10 first? I feel like if you're ever going to go seven, so like 13, 10, 9, 7. Actually, that's true. Well, that still means that 9 and 10 would occur before hitting 13. Because if 13 went down to 7, then it would just never be able to hit 9. So 7 would, so 13 to 7 just would never occur, right? Just would never make sense to jump from a high to a lower one and skip stuff between them. There's just a strictly better pattern for that. Because you're never going to be able to hit 9 in that case. So I think maybe I should just be tracking the nearest neighbor. The nearest neighbor that can jump from. The nearest left hand, the nearest right hand neighbor rather than a list. So like the nearest left hand neighbor for 10 might be 13 and 12, 7, 9, 10, 6, 10, 12. Okay, so it just should be 2 values. Okay. So it should just stop. So add the left neighbor. So for every index delta in range D, append it if it's there. And I think this should just be break here. Okay, and then this thing is also going to do that. Break. Alright, I'm going to go ahead and just double check that this is working still. Oops. So this thing can jump from 2, this thing can jump from 0 to 2, 4. This thing from 2, 5, nothing, 5, 8, 6, 8. Okay, yeah, that's fine. Okay, so reverse sorted. And then I want to from the lowest value to the highest value. Yeah, maybe this should just not be processed. Maybe this should just be 0. It's going to be 0. Maybe it should be infinity. It needs to increase. Maybe it should be -1. Just to know that if it's -1, then it hasn't been done. Otherwise, it should be, it's going to be storing this, the longest length to this index, longest path, or length of longest path. Okay. Alrighty. 0. Maybe it should be 0 actually. Maybe it should be 0. How do I know that hasn't started yet? Okay, well, let's, so 0, yeah, maybe actually should be 0. And then I'll do the process while process indices from lowest height to highest. So this is going to be while there is something in the value tuples. The value and the index is going to be popped from the stack. And then I would need to take the current length. The current path length is going to be processed at this index. So this is going to be starting at the lowest height, which would be 4 here. And then I want to jump to the left and right side and make their processed values to be 1 more than the current value. So for every neighbor in jumped from of this index, so the neighbor is the neighbor index, then I'm going to say that processed for this neighbor is going to be maximum of current plus 1 and whatever is currently there processed. Whatever is currently there processed for this neighbor. Yeah. So it'll go to here and set this to be 1 and this to be 1. And then the next thing that gets processed is this one. And it'll set these to be 1s. And then next thing will be processed might be this one, set these things to be 1. Processing this one, set these things to be 1. Or actually this one, set this thing to be 1. And this thing it'll process. Since this is current 1, this will make this thing 2 and this thing 2. Okay, I think this is correct. And then I just return the maximum of the process. Maybe maximum of the process plus 1. I think it should be returning 1 at the very minimum. Okay, maximum process plus 1. Okay. Actually probably could done without, if I just sort here. Yeah, this is a little slow. I think I could do without the value tuples array. I can probably just sort using a key rather than creating a tuples. Okay, yeah. Wow. For some reason these are not particularly hard, I guess. But I can get rid of the value tuples here because I don't actually use it besides using it for the index. Well, actually, I do need to have the index. No, but I can just use the key, right? I don't actually use the value. The value is just there for the indexing. So I think what I'm going to do is I'm going to say array sort reverse true key equals lambda x, where x is basically x is the index. No, x is the element. No, x is the index, right? Yeah, x is the sort the array. What am I thinking of here? I need to know the indices. I need to know the indices. So I guess I just need actually if I just need to know the indices where it occurs, I think I need to actually create a new array. I'll say this is the process stack. It'll go 0, it'll k for k in range n, and then process.sort reverse equals true, key equals lambda x, where x is array x. So sort the element, and instead of using the element as the key, use the array at this element, because the elements are basically indices. Okay, and then I'll just use for every while process. Then the index is just popped. I guess maybe current equals process at index. Yeah, I still need that. I think that's okay. Yeah, get rid of this. And maybe get rid of this other line. Let's just keep it for now. Probably should comment it out rather than delete the other one. Okay, same speed. Ooh, 25 milliseconds runtime. Wonder if I could have done this without sorting. Yeah, the slowness is actually probably coming from this, right? Finding neighbors. Finding the neighbors. Oof, 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 oof. Should I? Because I'm pretty sure if I just use a monotonic stack, it'll create the neighbors. I use a monotonic stack. Yeah, this is pretty slow. Because I just need to keep track of one left side neighbor and one right side neighbor. So if I kept track of a monotonic stack of increasing, so it'd be 6, 14, 6, 14, skip, 6, skip, 6. Hmm. 6, 4, 14. So it decreases and increases. I wanted to build the right side neighbors to actually keep a monotonic decreasing stack. Actually, so 6 pushes to 4, 14 would clear off, 14 would make itself the neighbor, make itself the from for the 4 and the 6. And then 14 would push 6 onto the stack. And then 8 would pop the 6, push itself in the stack. I guess when I push something on the stack, that means it's a neighbor that can go. When I pop stuff off the stack, then what? When I push things on the stack, then it would connect the thing that was, connect the thing that's on the stack with that being its right side neighbor. And then if I pop it off, alright, I think I'm gonna call this a my solution until I'm forced to actually do that second part to further optimize it. Okay, so I'll say this is kind of like a partial solution. Okay, so summary. No, this is not definitely not a fully optimized solution, and clearly shown in the kind of runtime distribution, runtime performance compared to other solutions. But I'm not feeling up to incorporating the monotonic stack to find the neighbors quickly at the moment. So in any case, for the above solution, the main components are for basically 1, create some data structure to link each index to its nearest left and right side neighbor within d distance, right? That can jump to it. Used a 2D array where the key or the index is the index, and the mapping is to the list of neighbors that can jump from it, or the nearest neighbors that can jump from it. So that was the jump from 2D array here, and the logic is that for or to create this, for each index, iterate to the left and right sides and stop at the first index whose value is higher than the current value, the current height of the height at array k, where k is the index that you're creating the list for. So it's this thing. Go leftwards, go rightwards. I extended the array so that it never goes out of bounds, even as I just increment the delta. And I break as soon as you can. This is where it could be optimized because you can use the monotonic stack to not have to do this process here. This process is basically n squared because d can be up to n, and you're doing a lot of redundant steps. If like you have too small stuff and you're going all the way to the end to find a jump point. All right, and then this is the part that can and should be optimized using some stack, some monotonic stack. The logic is a little tricky in my guesstimation. And then after that, process or create a process stack of indices sorted by lowest value at that index. Lowest value at index. And then process those indices in turn. Keep track of the longest path to each index when processing an index. Go to its nearest left and right neighbors that can jump from it, that can jump to it, and update its longest path if current path length plus 1 is better. So like your processed is the data structure that keeps track of the longest path to a certain index. You're going from the smallest index to the largest index, or the index with the smallest value to the largest value. So at the start it'd be processing like the lowest value in the array, and the kind of current path length is 0 because it basically can't have a path that extends it, or it can't really extend any path because it's the lowest, right? And then it goes to its neighbors and then updates its neighbors to say that 1 can be the path up to that neighbor because it can jump from this index to this spot to that spot, jumping from that spot. And then it keeps on going that until it processes everything. This is pretty fast because there's only up to 2 neighbors and you're processing each index once, so it's basically 2n or O(n). And then so time complexity is going to be O(n squared). Although the fastest creation of the jump from kind of array should be O of n instead of my inefficient method. So this in pre-theory should be O of n if optimized. And that's strictly based on my poor handling of this neighbor calculation. I think the processing thing is fine. The processing of the jump from array to calculate the longest path should be O of n as the above. Base complexities can be O of n. Oh, actually, yeah, it's O of n, since jump from can have a list that is at most two for each element, for each index in the array. All right, cool beans.